The youth of a developing country not only want to push our city onto the world map, but also Mars on the world map. We deeply want to be personally part of this mission. We design and develop most of the technologies that make up our robot from scratch. Our imagination is particularly simulated by the AI boom. We have created ML algorithms to make our robot as independent as possible on Mars, just as we try to be independent when building this on Earth here at the university in Łódź. It's our passion, gaining skills and experience, testing our solutions on the international or interplanetary area. Our team consists of over 50 people altogether. We are divided into fields and product groups. They are product managers, overlooking all the work, electronics, who construct all these parts, drone teams that build our drones, suspension team that build the suspension for the rover, mechanics that create and craft all the parts for the rover, IT who write all the codes and other things, and the sampler team that builds our samplers. We meet frequently, discuss all the ongoing work, exchange experience, and push our work further and further and further. The rover's power supply relies on 3 high current cell packs, which is why we place a strong emphasis on safety. The first stage of protection is the battery, which includes a battery management system module that monitors the current drawn and the voltage of each cell. This information is sent to the user, allowing us to determine how much energy remains. The PCB features overcurrent and overvoltage protection. Right after this section is a bank of relays dedicated to direct currents and those higher than the maximum generated by the battery. On the software side, our team has developed several safety systems. The motor stops when nothing is received on the CAN bus for more than half a second. The motors have to additionally be enabled by the CAN bus after being powered. The onboard computer checks the status of the steering application. It also prevents running other sessions of the application to avoid conflicts. The application uses MQTT protocol. When it is connected with the rover, it sends last will and testament messages to the broker running on the rover. It causes the first change in the status to failed and stops the rover when unexpected disconnection occurs. If the signal gets re-established, the status is being changed to active. In case of the connection with the remote controller being lost, it causes the e-stop signal to be activated and the rover stops. Additionally, if there is no activity from the controller side, the rover switches to e-stop mode. The deep probe design is borrowed from the previous rover and features 2 movable axes. The probe lowers to the ground, then a drill is activated to collect samples from depths greater than 30 cm. After drilling, we retract the entire drill and raise the probe structure. To collect a sample, we extend the sample container from under the rover. The containers have various sensors, such as a moisture sensor, a mass sensor, and a pH sensor to allow for quicker analysis of samples directly on the rover. We plan to collect 2 surface samples using the manipulator with a special modular head. The head rotates with one side designed to break up the hard surface of Mars, while the other side features a specialized gripper. Thanks to the innovative design, this gripper can handle various objects with unusual shapes, such as a regolith. The regolith sample and the surface sample will be stored in a special container, which also have sensor for analyzing the samples. These containers will be mounted on the rover's body. Currently, the project of this is about to be finished. The only thing missing for the probe is the mechanism for storing and collecting deep samples. To meet the requirements, we designed and constructed a new manipulator with 6 degrees of freedom. It is equipped with stepper motors, planetary transmissions, motor controllers designed by our team members, and encoders to read the position of the joints. All these components are essential for implementing a proper control system. Our primary focus was on reverse kinematics and the autonomy of the manipulator. This includes reading ERC codes, detecting and picking up science probes, and manipulating them using the operator panel. Additionally, we designed two end effectors for science and maintenance tasks. The first one is dedicated to operating the operator panel. It is capable of switching buttons, grabbing objects and precisely manipulating them. The second one, called the Jellyfish Gripper, was designed and developed by our teammates. The original strips can grab heavy objects with unusual shapes and structures without needing much force. All the force is provided by the strips. Considering the schedule of the video material, we are only able to make the first prototype of the manipulator without the drivers for the stepper motors. The software and autonomy are currently being developed in a simulation using the EROAS and Gazebo frameworks. These controllers are equipped with the following protections: against reverse polarity, overcurrent, overvoltage and temperature. We are able to power even larger engines, not only NEMA 17 but also NEMA 23. They also offer data transmission to the CAN bus. Each PCB is expensive, so we only delivered 2 at first. At the same time, they are enough to make the rover run. We also used the so-called black box. This is a BLDC motor controller adapted to our robot. To achieve optimal safety, we also need brakes. The current wheel design does not include gears, however they have significantly higher efficiency. If we want to use a safety that will be completely disconnecting the power supply and stop the rover in place, we need either brakes or wheels with gears. At this point, we are able to brake in an emergency, provided that it is supplied with power. If we stick to the engine currently being tested, we will implement a brake. If this solution ultimately turns out to be suboptimal, we will add gears. Therefore, we are currently able to turn the rover using the differential driving technique. It takes additional time to write the appropriate code to turn these wheels safely. This is also due to the fact that the stepper motor drive arrived much later than expected. As of right now, when we set a given angle, it is not always achieved. The cause is a currently unidentified problem on the communication bus. We did not want to install these controllers because in order to be able to test everything safely, limit switches must be implemented, which will ensure that when the axis reaches too large an angle, they will not allow further rotation and we will not break the wires. We implemented 2 safety buttons. The black one disconnects only the power part. It disconnects power from all engines. When testing various software solutions, we are sure that the rover will not move and can perform this test without having to leave the rover wheels above the ground every time. The second button is used to disconnect the power in the event of software or communication malfunction.